right. So my name is Henry. I do crypto research at the Zcash Foundation. Previously, I was working at Chain and then Interstellar with Kathy and Oleg. Together, we built like a really fast bulletproofs implementation and a confidential asset scheme and stuff that Kathy is going to talk about in a bit. But what I'm really interested in is building tooling for building proof systems. So before talking about some of those tools that I think might be good, I wanted to share a few kind of general thoughts. The first is that the problem space is evolving together with the design space. So if you look at the development of all these new zero-knowledge proof systems, it's pretty clear that like the design space of all possible proof systems is not really very well mapped out. And there's all these different proof systems that have different trade-offs. But those trade-offs are really only half the story because the trade-offs in the design space correspond to different potential applications in the problem space. And as we've seen, there's like all these sort of new ideas about use cases and potential applications. And so that's also not really very well mapped out. And an additional complication for zero-knowledge proofs is that the problem space is really tightly linked with the design space. So if you think about some other kinds of cryptography, like say like encrypting and signing a message, that's a piece of black box functionality that has a very clear definition. And cryptographers can go off and design like, hey, here's my signature scheme. You know, here's this other signature scheme. Which one is better? Or you can have competitions for specific functionality, like the NIST post-quantum competition. But zero-knowledge proofs don't really do that, right? They don't provide you with this like single black box functionality. They prove some relation, and that relation is a statement about some problem that an application is trying to solve. And it turns out that that proof system, or that relation, not only is that going to be specific to the application, but it's also kind of linked in with the proof system, right? So for instance, the sapling circuit in Zcash has an embedded elliptic curve, and the definition is actually tied in with the proof system that's being used to implement it. So that's a challenge. And there's a second challenge, which is that we still don't really know how to implement zero-knowledge proofs properly. If you look at the rate of change there, right? You know, I think that the Zcash company, not the foundation, has some of the like best ZK engineering. And if you look at the difference between like the first sprout circuit and the sapling circuit, right? There's huge improvements. And so we're still figuring out like what are all the best practices? What are the like, you know, how do you actually do large-scale engineering on these systems? And so because of that, there's kind of this concern, which is if you do like standards first development, I think that there's maybe a risk that you end up with a bad standard. So if the model is like, let's get everybody together and we'll decide what the problem is, and then we'll figure out a solution to that problem and like write it down in great detail in a standard, and then have people implement it, then I think that there's like a big risk that that might end up with some like suboptimal standard. And if you look at the history of like TLS or something, there's examples of like, you know, we don't want to make like the X509 of zero-knowledge proofs. So as an alternative model, right, you can have people like, you know, here's the problem that we're solving. We have some solutions. And now the people who have some interest in those solutions kind of get together and achieve consensus about how to do interoperability. And I think that that would be like a less risky model. So let's try making some good implementations first. And what I'm going to tell you about today are two tools that I think might help, at least in some small part. The first one is Merlin transcripts. So to tell you a little bit about this, right, what's the problem that we're trying to solve? Many of the people in the room may know about the Fiat-Shamir heuristic. Basically, we want to convert an interactive argument into a non-interactive argument. And if our interactive argument has verifiers messages or public random challenges, then there's this idea, OK, we'll replace those challenges with a hash of the prover's message. And if we like believe in our hash function and like random oracles are real and stuff, that's all good. So very cool, simple idea. But it turns out that this has like kind of like fractal complexity. The more that you look at it, the more there's all these like little details that come up. Like, first of all, what are the prover's messages exactly, right? If you read a paper, they don't really say, or how are they formatted, or what if you forgot some, or like what if this encoding was ambiguous? If you want to have domain separators, where do they go? And like, are you going to have a different domain separation mechanism for every single protocol that somebody implements? And if you have some protocol that requires challenges, like what happens if you need more challenges than bytes in the hash output size, and like how do you expand that exactly? And what about multi-round protocols, blah, 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 right? So, and like how do the prover and verifier meet anyway? Are they just like these abstract beings in some plane that met somehow, right? Or did they say like, hey, here's the proof I'm going to do, right? So the big takeaway from that slide is that that's really annoying and error prone. And hopefully the graphic design indicated that too. But what's the root of the problem? The root of the problem is that the proofs that people specify and analyze in their paper are interactive. But the proofs that people use and implement are non-interactive. And these are like slightly different concepts. And the translation from the one concept to the other concept is like left as this kind of like ad hoc thing that the implementer is supposed to just kind of like figure out, right? So unsurprisingly, this is a source of vulnerabilities. There were problems with the Helios e-voting protocol, ironically used for the IACR board elections, where some stuff was not included into the hash. And also, more recently, in this Swisspos Skittle e-voting system. And that one was apparently going to be used for real elections, so that's like possibly a problem. So what's the idea? The idea is basically like, what if this was automatic, right? What if we model a proof protocol as operating on a transcript context? And then we can use a cryptographic sponge to absorb prover messages and squeeze challenges. And because sponges allow switching back and forth from squeezing to absorbing, this is, handles everything very naturally. And we can implement our protocols as if they were interactive, right? So if you have a paper that says, prover sends LNR, you could just like write that in your source code. Very nice. And if you need to get a challenge scalar, you could just write that in your source code. And that would be very cool. So that's what Merlin does. This is this nice image that Oleg made with Merlin the Enchanter and the Ketchak, some graphics from Ketchak. It grew out of the Bulletproof's work with Kathy and Oleg. It's built using Mike Hamburg's Strobe protocol framework, which is like a kind of toolkit for building protocols. So Merlin is a specific way to use Strobe. It does automatic message framing for all of the prover's messages. So that helps with encoding ambiguity. And it gives you this nice minimal byte-oriented API. So if you want to use Merlin for a proof system, if you are sort of like closely thinking, you might notice there's a gap because I said like commit point and like challenge scalar, and those aren't bytes. But I said there's a byte-oriented API. And there's this problem that there's typed objects in the proof system on the one hand, and some transcript bytes. So what is the responsibility of the proof protocol? It's to define some transcript protocol of this is how my objects go into bytes for the transcript. And that's all the proof system has to define. And in Rust, it's really easy to define this all in like one nice place using an extension trait to add these methods. But other languages, you can do exactly the same thing. So hopefully that sounds cool. And there's some security improvements, maybe. But there's some other, in contrast to this thing where the more you look at it, the worse it gets. The more that you look at this, there's actually a bunch of interesting kind of emergent properties. So one simple one is that you can do transcript logging. So here's an extract from part of our test suite. And you can recompile with a debug flag, and it will dump the entire transcript log to standard out. So there's some initialization. There's a domain separator for our application. We're starting a range proof. You commit the public parameters. The prover sends their commitments. They get some challenges. And when you're debugging or developing some protocol, you can just like look and see what it's doing. So that's very helpful. Another thing is that you get domain separation by default. So if you remember that we're modeling a proof protocol as operating on some transcript context, then it's not that the proof function is going to create some transcript, but that transcript is passed in as contextual data, right? And so that means that the user of the proof function has to initialize a transcript, and they have to supply a label to do that. So what this means is that every application's proofs are going to be domain separated by default. So all of the users are steered onto this sort of nice best practices path where it's harder for them to screw it up than to do the right thing. Another thing is that you get automatic composition. Again, remember that we're operating on a context, but there's no requirement that that context had to be freshly created, right? So you could create a transcript and then declare, hey, I'm going to do 2 proofs. And then you do the first proof. And then you pass the same transcript into the second proof. And all of the second proof's challenges are going to be bound to the first proof. And all the first proof's challenges are going to be bound to this declaration of I'm doing 2 proofs. And the key thing is that this requires no changes whatsoever to the proof implementations that you're composing. All they have to know is I accepted this transcript context. And finally, there's another thing that you can do, which is proving with a counterparty. So one use case for zero-knowledge proofs that's pretty cool is if you have some protocol, and every time you do a protocol step, you prove that you did your step correctly, and you send that to your counterparty, then this allows transforming the analysis of the protocol from like possibly Byzantine to honest but curious participants, which is quite helpful. And the thing to observe is that if you have this transcript, then proving and verification are going to perform identical transcript operations. So if we suppose that we have 2 parties, A and B, and they've initialized some transcript with their label, party A will do their step and prove it, and then they send that off to party B, and then party B verifies, but that verification process will resynchronize party B's transcript with party A's. So now when party B does their step, they prove, send, party A verifies, and in this way, these transcript states sort of ratchet forward with each step of the protocol. And what's happening is that they're composing proofs of each step to give a proof of the entire protocol run. So by default, you don't have to worry about like, hey, what happens if a proof of one step gets like replayed into a different session or something like that. It's all very nicely tied together. And again, this just kind of is an emergent property. So hopefully that sounds cool, but there's like an extra thing. And the extra thing is there's these bad entropy attacks on, OK, entropy is a problem. So for Schnorr signatures, as an example, there's all kinds of problems where the signer has to generate a random blinding factor. If they reveal their blinding factor, then obviously that's fatal. And also if they reuse it, that's fatal. So maybe you're thinking like, I won't do that. I'm like much smarter than Sony. So also, if you leak just a few bits of blinding factor, over many signatures, that's also fatal. And like all of these attacks probably apply in general to all of these other zero-knowledge proof systems. So maybe you could ask, like, could we mitigate them generally? Yes is the answer. And one way to do this is using transcript-based randomness. So if you're a prover and you need randomness, you can build this transcript-based RNG. And the way that you do that is you clone the transcript state so that your RNG output is going to be bound to all of the protocol run, at least. And then you rekey the sponge with your witness data. So this is kind of like deterministic nonce generation. And then you can rekey with like your OS RNG as like an additional backstop. So what this is doing is it's using strobe to generalize Trevor Perrin's like synthetic nonce construction to like arbitrary proof protocols. And you get this like mostly for free if you use Merlin. So some current status, future projects. On implementations, there's a stable Rust implementation that's available on crates.io. I also wrote a single file C library targeting C89 that's intended to be easy to integrate into applications. And it's feature complete, but not like stable or secure or something, because like it would be good to actually do an integration first, right? And the spec and design docs already exist in the Rust documentation, but they could be pulled out into some separate thing. A future direction that I think would be cool is some kind of like spongy circuit thing, right? So using strobe shows you like concretely, here's how you can build an entire symmetric crypto framework from a single sponge primitive. So if you had a circuit-friendly sponge function, you could do all this symmetric crypto inside of circuits and only have to trust like one thing. And then you could maybe build like a circuit-friendly Merlin for doing like proofs and proofs. That'd be cool. And I have some ideas, but nothing real. So that's Merlin. And the second tool that I want to tell you about is this toolkit for doing Schnorr proofs. So what's the problem that we're trying to solve? Basically, the problem is that all these crypto papers just like want to use Schnorr proofs, but they don't just specify the statements. So they'll be like, hey, here's our protocol, and like at this step of the protocol, this participant attaches a proof of the following relation, right? Now, if you're an implementer, this is like kind of a problem because in the first case, let's say you don't know all about Schnorr proofs. Now you have to like go learn that, and it's like mostly folklore. Or even if you do, all these proofs are like actually like pretty annoying and tedious to implement. So what's the idea? The idea is like we could let implementers just like specify the statements. That'd be cool. You could write something. Let's just imagine you could write something in your source code like this. I want to prove an equality of discrete logarithms. Well, just like give a label, declare my variables and the statement, and like stick that into my source code. And what would I want out of this? I would want some kind of auto-generated implementation with a constant time prover. And it could automatically derive both single and batch verification, and then have like memory-safe serialization of the proof data to like any format that I would want. So that's what this toolkit does. And it actually has 2 levels of API. So there's this declarative specification mode, where if you know the statement that you want to prove, and it's statically defined, then there's this macro to do code gen. That's what the defined proof is. You specify a module where all your generated code is going to live. You give a label. You declare some secret variables, some public variables that are per proof, and some public variables that are common across proofs, and then your statements. And then what does that expand into? It expands into this imperative implementation. So it has a Bellman-inspired kind of constraint system idea for API for Schnorr statements. So you have all these variables, and you build linear combinations, and you feed them into a common constraint system API. You can compose statements at runtime, or you can define statements at runtime. So if you have like say a proof with a variable number of clauses in it, right? You could define that imperatively. And you can also compose together different auto-generated proofs into the same Schnorr constraint system. And finally, you can also compose these proofs with other systems. So if you need to like prove that some like bulletproofs input is actually an El-Gamal encryption of some other thing, and you have these extra things, then you don't actually need to do work to like define some custom extension for each possible thing that you might want to tack on. You can just like compose it together using the transcript. And that doesn't require any implementation changes whatsoever. So I think this is really cool because it lets you kind of like accelerate the process. So as an example, there's these, here's this anonymous credentials paper that uses like discrete logs to build an anonymous credential scheme. It's very cool. And in their paper, they say, to give you some concrete estimates of what this scheme performs like, we implemented a particular proof statement for credential presentation using like a custom multi-X with OpenSSL and P256, and right? But now, right, this generated implementation requires no effort beyond writing the statement. So that's like much faster. And that is going to like accelerate your development process. But it also, the implementation is accelerated because the generated implementation, like depending on the backend, has like 20 to 40 times faster timings than the paper's numbers. And so all of that optimization work is going to apply to every single protocol that anyone uses, right? So it applies to the bulletproofs implementation. It applies to these generated Schnorr proofs. But any kind of statement, they all pick up on that common library work. So yeah, I think that's pretty cool. That's the end of my talk. Hopefully this sounds interesting. If some of those tools sound cool, then you should go try using them. and report back on the things that work and the things that don't before it's sort of like too late to bake in all the bad decisions, because I'm sure that there are some.
Okay, we have time for questions. Any questions on this? So let me ask a question. So Merlin is basically a way to kind of bake in the future mirror heuristic and implement it efficiently. So it's not difficult to give examples of multi-round protocols where the future mirror heuristic actually fails. It's insecure. So does Merlin do anything to protect the developer from saying, hey, you're using a protocol here where you should be careful with using future mirror?
Not really, no.
I see.
Yeah.
Maybe that's something for
could be
work.
in the future.
Yeah. Cool. Great. Yeah, please.
Hi, my name is Michele. My mother's name is no joke. That's very cool. One of the things that I wanted to do on the long run, and this is so perhaps a question for you and the rest of the Zcash people, is that in all these multi-party computation protocols, you have often these interactive parties that are talking to each other, and often they can abort, and you don't really have a way of saying, oh, this message should have been sent after this one, like a finite state machine. You don't have a way to model this as a finite state machine. You don't have a way of saying, now this party is aborting and never talking to anybody. You don't have a domain separation. And so have you guys thought about having a library for doing these sort of things? Because I think some of these ideas should really be brought also to the MPC world. And so this is my question.
So for the Merlin transcripts themselves, the target concept didn't include like MPC, so that could be done, and it would probably be a good idea. But at least like as it exists, it's just scoped for like how do you implement proof protocols easily. But yeah, that would be great.
Cool. Other questions? Yeah.
So Mike Lauder, Sovereign Foundation. So with anonymous credentials, you typically have various signatures over various attributes, and then sometimes you want to link those attributes to other proofs like range proofs or set memberships. So how would you build something where you describe this is the signature I'm using for the proof of signature knowledge, and then I'm revealing these attributes, I'm hiding the rest, or I'm doing range proofs on these ones or set memberships on these ones? Would Merlin be able to do that as of right now, or is this more of a future work?
So I think it ends up depending a little bit on like the details of the scheme. So for instance, the like example that I mentioned, right? In that scheme, the output of the credential presentation are a bunch of Peterson commitments. And so if you wanted to like link that up with like a range proof, for instance, you could like feed the output commitment as the input to a bulletproof, but that is kind of something where you have to, there's like some amount of glue that you have to write yourself, and it depends on the actual construction. I don't know if there's going to be like ever a kind of do everything construction.
Okay, great. All right, so it looks like we're out of time. So thanks, Henry. This was really cool. Keep up the good work.